to the tutorial on analyzing your HLA data. Now, you might think, why do I need to be able to analyze this data manually when you have tools to do it? And I think there are several good reasons why it is good to look into the data. And I'll just give you a couple of them, and I'm sure that there are others as well. So first of all, I'll just open the data in Bioedit so that you can look at it while I'm talking about this. First thing is that when you design an assay, even if you're going to use off-the-shelf tools to analyze that data, there are times when you'll run those tools and you won't get the results that you expect. Maybe you'll get no result whatsoever, or maybe you'll get a result that seems to have used very few of the reads that you have. And if you know how to look at your data, you can then go, is this not working because there's something wrong with my data? And you can open up your data set and go, yes, that's what I expect, or no, there's actually something with the data which is causing this issue. It's not the analysis, it's certainly the data. So looking at the data here, it looks like a bit of a jumble, but as we go through this analysis, you'll see that this data makes a lot of sense. And the second reason why maybe it is a good idea to be able to look at these data files is that as you go through your career and you start developing your own assays, you'll need to be able to analyze the data that you create. And analyzing the data you create will require you to understand the data that you're creating, and then either based on that data choose the appropriate tools and set them up appropriately, or maybe write some tools yourself or instruct someone else to write those tools. And all of those things require some understanding of the data. So now we've opened up this data file, which is a subset of the data from an HLA run, and it contains a small percentage of the reads from 3 samples. So the actual data set is much larger. You see here this data set is only 4,000 total reads. And when you look at it, to me, it looks like a jumble. But actually, as we work through this, you'll see that it's actually very well organized. So as in the lectures that you had, you saw that the reads we have here are a collection of reads from a group of samples which have been pulled together, and each sample has been tagged with a mid tag, and that tag is 11 bases long. So if we select those first 11 bases, in Bioedit there's the ability to sort all of these reads by those first 11 bases that were selected. So if you go to the sequence menu, go down to sort, just almost halfway down, and then we choose by summed residue frequencies in the selected column. It actually means selected columns, those first 11 columns. And when we sort by that, suddenly it looks a lot better. It still looks like a jumble after those first 11 bases, but the first 11 bases are all uniform. And we can make this uniformity stand out even more by clicking on this button here, which basically makes all bases which are the same as that base position in the selected sequence, in this case the top sequence, be replaced by a dot. So you can see there it's very clear that all the sequences on this page have the same first 11 bases. And some of the reads you can see, this one here for example, have pretty much the same bases all the way across the page, but most of the reads don't. And the reason for that is that these are just reads from the same subject. They're not all reads from the same amplicon. They could be from different exons, they could be either a forward or a reverse read, they could be from different genes. So now what we've done is that we've now sorted these, and we can choose all the reads which belong to the subject which was tagged with this mid tag, the ACACGTAGTAT mid tag. So what we'll do is that we'll select the first read by clicking on the read name, scroll down to when we find the bottom one, and as I said, this is a subset of the reads which belong to 3 samples, so roughly we'd expect about a third of the reads, hopefully, to belong to each sample. Obviously that Wouldn't always be the case, but we've been quite generous in giving you 3 reasonably matched. And so if we scroll down to about a third of the way down, we see actually it's probably just a bit more than a third the reads belong to this mid tag. Whoop, just gone too far. And then you just hold down the Shift key and click on the last read that belongs to this mid tag. And now they've all been selected. Go to the Edit menu and copy all the sequences to the clipboard in FASTA format. And you get an error message. The error message says that there are more than 1,000 sequences selected, and this program was written probably at least 2 decades ago, and back in the days that it was written, it was felt that it was too slow to copy more than 1,000 sequences at once. Things have changed. Computing power is much, much greater now, but unfortunately that's just a limitation of this program. So what we need to do is that there are 4,000 sequences in total, and we can see that this is clearly the scroll bar is less than halfway down, so we know we've got less than 2,000 sequences here. So we'll just copy it in 2 bytes. So if I just click on the one below the one I wanted to unselect all those, click on the bottom one, and I'll go approximately halfway back towards the top, hold down the Shift key, click, selected half the sequences roughly, and then I go copy all sequences to clipboard FASTA format from the Edit menu. Then I'll go to a text editor, make a new file. I'm using PSPad here as my text editor. You can use Notepad, you can use WordPad, you can use whatever text editor you want. It's better to use a text editor than to use a word processor, because often word processors like sticking in extra funny little symbols which you can't see and create a mess. So I'll paste those in, and I'll just push return to start a new line. Go back to BioEdit, click on the next sequence above, scroll all the way to the top, hold down the Shift key and select the top one, edit, copy sequences to clipboard FASTA format, back to the text editor, and paste those in. So now I have, if I look here, there's 2,814 lines, which each FASTA sequence takes 2 lines, so there's going to be 1,407 reads which belong to this sample identified by the mid tag ACAC GTA GTAT. And to find out which mid tag that is, if I had a file which mapped that mid tag to a sample name, I would go to the mids file which you've been provided with, and I see that ACAC GTA GTAT, just confirming here, ACAC GTA GTAT corresponds to mid 2. So if I just save that as mid 2.fasta, and then I would go back to this file. I'm not going to do it here for you to watch, but I will go back to this file and scroll down to where the next mid tag starts, and you see here that we have 3 sequences which don't really seem to form part of a group. They're probably just caused by sequencing errors. So I would start with this read here to form the next group, and to make this one get all of the dots, you right click on the sequence name, and that makes that the master sequence. So you can see now that the dots are below here, and I would then copy all of those into a text file and save them as the appropriate mid name, and then I would go down and find the third group and copy those out and save them. Thank you.